This audio abstract was created and produced by Arcadis. All statements, opinions, interpretations, and conclusions expressed belong to the individual speakers and do not represent views or policies of the Groundwater Monitoring and Remediation Journal, Wiley Publishing, Arcadis, or any other entities. This is Craig Devine. I'm here with Mark Killingstad to talk about our recent article, The Plastiverse Extends to Hydrogeologic Systems. Microplastics are important emerging groundwater contaminants. Microplastics are an emerging contaminant whose evolution parallels that of another recent emerging contaminant, per and polyfluoroalkyl substances, or PFAS. Microplastics and PFAS are similar in that both are categories of highly persistent and ubiquitous compounds whose diversity and toxicity have limited understanding. For more than a decade, plastic production has been increasing at an average rate of 4% a year, with nearly 400 million tons produced in 2021. This astounding and historical projected production of plastics and associated waste management has driven the widespread distribution of microplastics in soils, biosolids, wastewater, stormwater, rivers, estuaries, oceans, air, and groundwater systems. Some are calling this new era the Plasticine. Mark, thanks for joining us. Before we get started, maybe you could give a background and an introduction to yourself?
Sure. Mark Killingstad. I've been with Arcadis for almost 25 years now. I am a hydrogeologist / groundwater hydrologist. I currently head up the community of practice for hydrogeology for Arcadis North America, and started out doing mostly groundwater modeling, fate, and transport of contaminants.
Lots of folks have heard about microplastics. What are they?
So microplastics are basically very small fragments of plastic, and we're talking about on the millimeter to micrometer scale. They're synthetic polymer particles. They can be fibers, they can be spheres, they can take all sorts of shapes and come from a wide range of sources.
And what are the origins of microplastics, and how do they get into the environment?
They kind of fall into two categories here. So you've got your primary microplastics, which are produced for specific products and applications, a lot of which goes into, say, cosmetics and pharmaceuticals. You're also talking about like polyester for clothing as well. So those would be what we would call kind of the primary microplastics. Secondary microplastics come from kind of what we would call macroplastics, or the larger plastics that, are part of our everyday lives. The plastic bags we get at the convenience stores, and when they break down in the environment, which they invariably do, mostly through UV light, they release and fragment into small particles, and those would be your secondary particles, microplastic particles. The source, certainly mismanagement of the waste, but they can also be kind of unintended consequences just from, say, agricultural fields where they'll use plastic mulch, where they will apply sludge from wastewater treatment plants that contain these microplastics in it, and they can eventually leach to groundwater. Of course, you also have runoff conditions. So essentially, they can enter the water cycle in many different ways. And once they enter the water cycle, they can become introduced to groundwater as well as surface water, oceans. And I think that's really where a lot of the research has focused on microplastics, is surface waters, and not so much on the groundwater side of things.
Yeah, I think that's a good point. I think a lot of folks would intuitively understand that microplastics are present and can be transported in various surface water bodies, particularly those close to human activity, like streams and lakes and estuaries, and ultimately into the ocean. But I think it may be surprising that microplastics have been found in groundwater systems. Let's talk a little bit about how that happens and characteristics about their fate and transport in those systems.
Agricultural fields can be certain sources of microplastics just from the application of treated sewage sludge as fertilizer on agricultural fields, the same way that PFAS has been introduced in a lot of areas as well. Microplastics can be introduced, particularly when they get into the soil. Then you've got all sorts of things that can start to happen to it in terms of the interactions it can have with the soil mineralogy, the microbial population, temperature practices that are used in farming in terms of tilling that can then get those microplastics further into the soil and then potentially leach and percolate down and reach groundwater eventually. So that is certainly one way that they can be introduced into groundwater. And then the other way is certainly the groundwater surface water interaction. So we know that surface waters are very susceptible, and there's been a large amount of research done in terms of the occurrence of microplastics in surface water. And then once you get to that groundwater surface water interface, of course, there's a lot of back and forth, and microplastics can be introduced to groundwater in that way as well.
So microplastics cover, of course, a lot of different chemical types, but also the size characteristics of microplastics range from several millimeters down to single digit micrometers, or even smaller if you move into the range of nanoplastics. So how does filtering in a porous media setting play a role?
Yeah, so it's interesting because that's been the thought in the past that subsurface would actually act as a filter. And to a certain extent, there have been a few studies that have shown that if you introduce microplastics almost as kind of a tracer test and, monitor down gradient, that you would see them show up. Just like a lot of contaminants, you see some attenuation that occurs. And the thinking is that, these microplastics get caught up in the pore space, either because of their size or because of, internal attractions between different particles. They become heteroaggregates if they combine with other materials, soil minerals, other contaminants, and they can change shape and size.
It's clear that, for the very large size particles, filtering would be important for porous media, but maybe we need to rethink the importance of filtering for coarser grain porous media, particularly with the particle sizes when we're 50 microns or less, which could readily move through typical pore space in a sand aquifer. And then, of course, the filtering behavior is much less present in fractured rock or even karst settings.
Yeah, absolutely. I mean, in karst settings, you're basically talking about open channel flow at that point. So it's essentially a surface water type system.
Can you describe what's driving some of the interest and the concerns from an ecotoxicological standpoint?
When you think about how plastics are made with the polymers and the additives, the plasticizers, various chemicals that get put into the plastics that we use for changes in properties to make them more flexible, to make them more pliable. Well, all these polymers can leach out as well. So not only do the microplastics themselves become a contaminant, but they also become a source of additional contamination through leaching of these chemicals. And primarily, these are the ones that, from a human health risk standpoint, these are the ones that have that toxicity, are the things like the phthalates and the bisphenols and the things that we hear about. Those can leach out from those particles. On top of that, then you've got the potential, because of the electrostatic interaction between microplastics and minerals and other contaminants, means that they can start to heteroaggregate with things like PFAS or PCBs or viruses and even bacteria. And, pretty much anything that you can think of will or could potentially attach to these microplastics. So they become vectors for co-contaminants on top of everything else.
In terms of understanding their transport, do we know enough to make reasonable predictions about their potential to transport in various systems?
Because they are colloids, they kind of follow that DLVO framework, which is good because it does at least provide this, scientifically tested framework for understanding and trying to predict their transport. But to me, the issue is that they're not true colloids because they can transform, as we were talking about earlier, from aging and degradation, and then through heteroaggregation and adding even potential contaminants. So, it's a little daunting to think that we can apply at least the existing models that are out there to accurately predict what is going to happen with these particles.
So we're still getting our arms around this issue and the prevalence and significance of microplastics in groundwater systems, but I'm wondering if you've got any thoughts on potentially applicable remedial methods and technologies.
So there are certainly, when you think about it from the perspective of the things that make microplastics difficult to deal with or predict in terms of their fate and transport in nature, from a treatment perspective, you can almost take advantage of that. So certainly things like physical methods like sedimentation, filtering, coagulation, flotation, things like that. And then there are more advanced methods that are out there that have been tested, things like advanced oxidation, primarily looking at techniques like photocatalysis, and membrane technology is also out there. Microbial degradation certainly does occur and has been used and has a long history of being studied for that. There are certainly a lot of studies out there that do indicate that combined methods may work well. Things like MBR, which is membrane with bioremediation, seems to work really well. And that is certainly something that is being looked at and explored.
So, Mark, going forward, what are some of the most important and pressing needs and research areas of focus for us to better understand this problem and address it?
So, first and foremost, I think the biggest issue that I've seen with microplastics is, and there's certainly been a number of articles generated about this, is that there needs to be a standard approach for how we are sampling, how we are identifying. Right now, there isn't a standard in terms of reporting. And so until that happens, it's going to be very difficult to make any sort of real progress. And increased interest, certainly, in the area of co-transport behaviors. When you look at it along the lines of PFAS, there are a number of papers that have been published that demonstrate that PFAS does adhere and attach to microplastics and can be transported along with it, as well as heavy metals, as well as nanoparticles, as well as bacteria, viruses, PCBs, PAHs, you name it.
Well, this has been a great conversation, Mark. As we wrap up, is there anything else that you'd like to add that we haven't had a chance to touch on?
I think we're in for a real eye-opening once we start looking at the occurrence of microplastics in all media, not just surface water, but groundwater, the atmosphere. It is truly all over the place. In fact, plastiglomerates, they've been finding that plastics actually have started to chemically bond with rocks and soil. And so the new geology is plastic and rocks.
That's fascinating. Well, thanks again, Mark. Really appreciate your time, and thanks for your efforts on this article.
Oh, you're welcome. Thank you.